Welcome to this 12th lecture video for Physics 4A. We introduced the last time energy as a conserved quantity. In this set of lecture videos, we will cover what we need to start using energy conservation in physics problem solving. To use the concept of energy in physics problem solving, we first need to introduce work. Just as speed and velocity were everyday words we have taken to give specific technical meanings, meaning that you couldn't use them interchangeably in this class, as you might in normal English. In this class, work is now a word with a very specific technical meaning. When we say work in this context, and not in context like, please go work on your homework, we are referring to a physical quantity that we define as force times displacement. And because force and displacement are not mere numbers, but vectors, that is, their directions are meaningful part of their definition and description, this multiplication has to be done very carefully and very mathematically. We defined and described the dot product earlier. Your textbook covered the dot product in chapter 2. We covered the dot product in the last lecture set. Dot product takes two vectors and gives a single number, a scalar. Using this mathematical operation, pronounced A dot B, we define work as F dot delta X. That is, force dot producted with the displacement. The new mathematical operation takes some getting used to, but once you are used to it, this is a fairly simple product. So, why do I say we need to introduce work in order to use energy in problem solving? It's because of the physical significance of work. Work gives you the change of energy. As a first example of this claim, you are going to see the work-energy theorem, or as I prefer to call it, work-kinetic energy theorem, which shows that net work done changes the kinetic energy of an object. And even more generally, whenever you see energy of any form changing, you can identify some work being done somewhere to cause that change of energy to occur. Because doing work is how we change energy, we need the concept of work to earnestly use energy in problem solving, where energy of an object might change or be transferred from one object to another. So, in the following videos, we will first look at the work-energy theorem derived in the textbook, and we will look at an algorithm simulation which illustrates the connection between work done, force times distance, and the change of kinetic energy. This is an example we will return to once we introduce the second conserved quantity next week, so please take note of the details. Then, we have about an hour-long lecture on conservative forces, how they can be distinguished from non-conservative forces, and the derivation of forms of potential energy of the two conservative forces, gravity and spring force, using the work done by the conservative force. And we will wrap up with a couple application examples. One is more of a justification for a simplification you will see me often use in working with vertically oriented springs. The second is a return to a question you might remember seeing in kinematics, and how the idea of conservation of energy can be used to greatly simplify our problem solving. Now, we will save the more interesting examples of conservation law problem solving in lecture until we have introduced the second conserved quantity next week. In the meantime, for specific help with any homework questions, please look for the additional problem solving videos provided elsewhere in the course. The other thing is the They keep saying energy theorem. It should be really work kinetic energy theorem. It's one of the few mathematically rigorous thing that you see in this class, and you the hint that this is a mathematically rigorous thing is that there's the word theorem, meaning it's something that it's mathematically provable. I don't know if this is surprising, but Newton's laws cannot be proven. There can't be any theorem for Newton's second law. Newton's laws are better described as postulates or axioms. Those are our starting place. We assume those things so that we can develop a mechanical description and analyze things. Um, the work energy theorem is something that can be proven once you have a definition of work, which means you have definition of force, so you have Newton's laws, and I guess I'm a little bit ambivalent about the other side of this thing, where do you have definition of kinetic energy, or is this a way you would derive kinetic energy? My own personal bias is that this is how we derive an acceptable form of kinetic energy. It goes down to really the definition of energy. You might have seen the definition of energy as ability to do work, but the truth is energy is an undefined quantity. We or it's not a precisely defined quantity in physics, in science. We define energy or we define expressions for energy in such a way that that it'll be conserved in all interactions. And when once you limit it to mechanical energy, you can't say it's always conserved. But with the mechanical energy, there are still contact parameters you can put around the situations to say if these criteria are met, then mechanical energy is conserved. So that's really the only thing we hold on to for energy. And the derivation that they go through for the work kinetic energy theorem is one that's showing, well, what form should the expression for kinetic energy have so that so that work done transfers to kinetic energy. I guess the way your textbook and really the standard presentation presents it is they introduce kinetic energy first. They give you this as the definition of kinetic energy, which is fine. It's not wrong. Once you have accepted this as a definition of kinetic energy, then work energy theorem it's a provable theorem that you can prove that. So this is how we describe work, and um, and this is the important thing to note when you have a network being done on an object. And when we say network, it's the work that we associate with the net force. So you have to be careful to include all the forces, both the applied force and any other force that you would introduce as you do force analysis. So when you have a work done that's associated with that net force, and over any finite interval going from point A to point B, you calculate the network. Then what you find is that network calculated is equal to the difference between how much kinetic energy the object has at the final point minus the how much the kinetic energy that object has at point A. And there are some um, um, nuances about the calculus operation here, and I think it's for at the level of this class, I think I'm fine leaving it here. So this is the kind of notational abuse that you might see a physicist engage in, which is so here, this is the expression that comes from just saying, so this being acceleration, this whole thing is the net force. So it's a net force, the product with the displacement. So you have this infinitesimal differential. So you have dW is mv dot dv. And you're trying to integrate, find the antiderivative, and the kind of thing that physicists would be comfortable with saying is, okay, I'm looking for an antiderivative, so I'm looking for a thing where if I take a derivative, I'll get this. So so if I have 1/2 mv squared, where v squared means actually, I think I can even do this. Let me, while I'm abusing my notations, let me be even more thorough in that abuse. So let's say this is my guess for the antiderivative of that. And if I imagine taking just a derivative or differential of this, then I would say, okay, 1/2 m, those are all constants, so I have 1/2 m. And okay, these are now my variables. I need to take a derivative. They look like a product, so I can probably use a product rule. So let me use product rule. So I have the derivative of the first one, product with the second one that hasn't been taken derivative of, and then plus derivative of the second one, or the first one, that product with the derivative of the second one. And as I was talking about earlier, that products, they commute. So these two are the same thing. So I can just say these two will simplify as 2 times one of these. And the 2 cancels this, and I get m. Let me keep this one, v dot dv. So, oh, this looks same as that. So yeah, this is my antiderivative. And I'm pretty sure I've done something wrong notationally as I'm going through this. But the reason we engage in notational abuse is because it ends up in correct expression. So there's some detail of how to handle these calculus things properly and correctly. And for the purpose of this class, we don't really worry about it all that much. Really, the thing that's important for us is the end result, this outcome, or the thing that's being proven, that when you have that you can draw an equivalence between the net work done, as in work being done by all the forces together, and the difference in the kinetic energy. And it's really worth emphasizing the work-kinetic energy theorem. In chapter 8, we are going to be introducing potential energy. And once we introduce potential energy, then you do have to be careful. You do have to be careful. So the theorem is proved in the context of where this is a net work. So it's a work including even the work being done by conservative forces that we're going to talk about in chapter 8 as part of this week. So this network includes all that. And the energy difference part, it's concerned with the kinetic energy, not potential energy, not other forms of energy, just the kinetic energy. And that's not quite the common approach we take later on, especially after we've introduced potential energy. So I want to make sure that you are fully aware of the limitation on when this theorem applies. It connects difference in the kinetic energy with the net work being done. So yeah, that's basically it. And oh yeah, and this is the kind of connection of what you see now with what you have seen before. The v squared formula, it's basically it's equivalent to the work kinetic energy theorem. You take the v squared formula, multiply it through by 1/2 m. That basically gives you what v squared formula was saying before. So this is a setup that's describing a cart of some mass resting on some level track, being pushed with a straight line with some fixed amount of force, and it says it's pushed for this distance. Now, this kind of setup, it's one of those things that's easy to describe it in words. Now, if I wanted to do this as an experiment, it can be really challenging. Applying a fixed force of 2 newtons on a moving object, that can be challenging. In a simulation, it's a lot easier. One, I can have a cart or something that's cart equivalent. That's ideal. I can just say no friction anywhere, so that if this thing starts out with any kind of initial velocity, let me give it some initial velocity, then it'll go on forever. It won't ever stop because there's no friction. Well, maybe it might stop eventually due to air resistance, but aside from that, it won't stop. And does it still have, okay, let me just zero out the velocities. And what simulation is nice for is I can apply a fixed amount of force in a way that's a lot harder in a physical setup. I have a thruster that can literally apply, well, 2 Newton of force, and let me give it a little toggle key so that I can turn it on and off. So I have, let me make the material 1 kilogram, since that's what the question said. And I can, so with the toggle key, I'm going to press T. I can apply a force for a fixed situation. So, so this is, I guess, the setup I want you to describe. And describe now and come back to it in about a week or two or so. So I'm going to just put this down as a marker. Want this blue to the background. Let me clone it. And with, I don't know if a cloned thing is also glued to the background. Oh yeah, it's glued. Okay, so I have this set up, and I can time this thruster so that I turn the thruster on when it is here, and then as the front of this reaches this end, I can turn the thruster off. That's basically what this question is describing. Kilogram resting, apply force of 2 newtons, push it for this distance. I didn't measure a meter, but let's say that's a meter. Yeah, might not be, but let's say this. So I'm gonna use by the way, I can control this with a space bar, so I'm just gonna do that. So let me start the simulation and just let this run for this distance under that fixed thrust. So that's one. Now, just to make this easy, let me do a plot. Show plot, and I'm going to plot x velocity of the object. And yeah, let me run this again. So running simulation, thrust to start, and end. Okay, let me take a screenshot of that for comparison purposes. And this is what I want to compare this to. I'm going to make the mass, instead of 1 kilogram, let me make it 2 kilograms. So I'm just gonna undo, go back to here. Oh, I think I can actually compare it here as well. So let me make the mass 2 kilograms. And let's do the same thing. I'm gonna keep everything else the same. I'm going to turn the thruster on here, and then I'm going to turn it off when the front gets here. Oh, I didn't time it right. All right. So this is the setup we have. And let me just copy this over. I guess I didn't really need to. Yeah, this one plot actually has everything. So you see that with those two masses of different, two blocks of different masses, you see that the final speed they reached is different. And these are the kind of questions that you could ask. So at the beginning they had the same energy, 0 kinetic energy. At the final ending velocity, they have some kinetic energy. So people could ask the question of, how do their kinetic energies here compare? And the answer, I guess, to spoil it, is that they have the same kinetic energy. And I can say that confidently, even though they have such different velocities, And you know, you can, if you want at home, you can do the math yourself. You see that one had a mass of 1 kilogram, so this had a mass of 1 kilogram, and it had a final velocity of about 4.4 meters per second. And the other one had a mass of 2 kilogram and final velocity of 3.1 meter per second. And if you do the calculation, kinetic energy, 1/2 m times v squared, these two should end up pretty close. And I can say that without doing the calculation myself, because the way this situation is set up, the way I apply the force on those two blocks, it's designed to do same amount of work from here to here. And I'm saying that even though, or maybe because, the amount of time I'm applying the force over is different. And this is the one of the ways people can ask tricky mechanical questions. And it gets even trickier when we have two different quantities of motion. This week we have kinetic energy. Next week we'll introduce momentum. And so let me bring this setup next week to maybe introduce some sources of confusion, and we'll have more chance to talk through in detail. But I want you to introduce this now, because we are talking about work and energy now. And when I was looking at this question, I thought, hey, I can actually extend this with the momentum and make it confusing. So we'll address the confusing part next week or the week after.
All the forces that we have been describing, we have talked about different types of force: gravity, normal force, tension force, friction force, and there's, I thought there was some more, spring force. All these forces that we've been dealing with for application of Newton's law. So we want to categorize those forces into two different distinct categories. What we are going to call conservative force, and what we are going to call non-conservative force. And I think this is the example we ended the class with last time. I gave example of one conservative force, gravity. So if you have a ball and I throw it up and it comes back to my hand, this is an illustration of how gravity is a conservative force. Do people remember? Yes? We did end the class with this on Tuesday. And I used the example of friction as an example of a non-conservative force. So when I push this cart on its side, not on its wheels, when I push it this way, then so as this cart comes to a stop, that's an example of how friction is a non-conservative force. And I don't think we got to, we ran out of time there, so we didn't have time to talk about what makes a force conservative, what makes it non-conservative. Good. So let me write down those two examples on the board so that we have something concrete to think about. So gravity is an example of conservative force, and friction is an example of non-conservative force. Let's go through more examples and try to figure out if they're conservative force or not. So let me write down the whole list of all the different types of force we've been dealing with so far. We've been dealing with gravity, friction, and we have a few more. Tension force, spring force. Anything else I'm forgetting? Normal force, thank you. Normal force. Anything else? I think in terms of types, this might be it. Let me just write down one more as a category of sort of applied force. So let's try going through each of these and see if they are conservative force or non-conservative force. So gravity and friction, we already put them into these two categories. Tension, is tension a conservative force or non-conservative force? A lot of people think it's conservative because you are thinking of this. I have a pendulum, or I'm going to have a pendulum, and so here tension force is in action, right? And this was one of the examples of conservation of energy I used on Tuesday. When I hanging to the side and let go, so tension force is acting the whole time, and you see the energy being conserved. So you want to associate this with the conservative force, right? That's where your intuition is coming from. What I want to tell you is that tension force is actually not conservative force. Let me illustrate. So I can actually put more energy into this ball using nothing but tension force. Right? I mean, so my hand was moving, so you have that. But the way that force was applied to this ball is through tension force alone. So on this ball, nothing but tension force is acting. But using nothing but tension force, you can change the energy of the ball, which means this is not really tension force is not a conservative force. So let me put tension force down in the second list here. What about spring force? So spring force, so I guess, yeah, so you're used to thinking of spring force and tension force being similar. They are different in one particular way. So if I hang this here, if I hang this here, and there's tension force acting on this somehow, and if I hang this spring here and hang a little bit of mass there so that it's not just a spring. So in many aspects, these two forces, you're used to thinking of them as similar. They are both a pulling kind of force. But there's one important way in which tension force and spring force are different. Can anyone tell me what that one important way is? So with the spring force, there's a mass. But I could have hung, I could have hung another mass here. So it's not a matter of how much mass is hanging there. But actually, as I'm doing that, maybe you will notice something. So let me hang more masses here. So I'm going to hang more masses here. Watch what happens to the string here. And let me hang a little more mass on this spring and watch what happens here. Do you see an important difference between the spring and the tension force? What's one important difference? Yeah. With the spring force, you see the change in length. So with the spring force, you have a way of telling how much force I'm applying. In fact, we haven't gone into detail about the spring force, which we'll do later today here. But the way I've been using spring so far in class was I was using this to illustrate how much force I was actually applying. So that's one important difference between spring and the tension force. With the tension, no matter how much force I'm applying, you won't really see it. I mean, the string might break at some point, but until that happens, or until it goes completely slack, you can't tell from this picture if how much tension force there is. And that will be an important distinction when we actually go into what makes a force conservative and what makes it non-conservative. So with the spring force, let me put it in the category of conservative force. And we'll see that the property I was pointing out here will be important in determining why spring force is conservative, whereas the tension force is not. All right, two more forces. Normal force and applied force. I guess one of the ways I would apply force is through normal force, but so normal force. Is normal force conservative force? Yeah, so a lot of people so normal force and tension force, I think the intuition that a lot of people have for these two forces are similar, in that you see these forces in a lot of contexts where energy seems to be conserved. So you associate with this energy being conserved, which is not wrong, as in, let me give you an example involving normal force where energy is conserved. So I have these tracks. So when this ball is on this track, there's normal force between the ball and the thing, right? Now, if I start the ball here and let go, then the motion you see, well, I mean, it's going down because of friction. But imagine ignoring friction. When you imagine ignoring friction, then the motion you see is consistent with the conservation of energy. Right? So that's why a lot of you would want to associate normal force with conservation of energy. But watch this. I can actually put energy on this ball using nothing but normal force. Right? So normal force can be used to put energy into this ball. And what that means is normal force is also not a conservative force. And when we get to the actual criterion that makes a force conservative, you will see that more easily. So normal force is not a conservative force. And the final applied force, I'll just give you a quick description. It's a sort of, what I mean by applied force is force like this one. I have this cart here right now, right? And right now, there's gravity and normal force acting on the cart. Its energy is not changing. When I say apply the force, I mean, really apply the force. Like if a question tells you a force F is being applied on this cart, either by me pushing it, or it could be by me, using friction. So there are different ways I might be applying the force, but the idea is that there's some particular force that's specified on this cart. That's not given by that's not necessarily from one of these forces, but the problem simply tells you there's some external applied force of force F. And when you look at this example here, applied force also doesn't conserve energy here. This cart right now has zero kinetic energy. And once the cart, so it starts moving because I'm applying a force. So when it starts moving, then now it has non-zero kinetic energy. So any kind of applied force would also fall in the category of non-conservative force. So applied force. So we have these two big categories of force. And so I should tell you this now. Actually, these are the only conservative forces you will see in this class. There are no other conservative forces you'll see in this class. So what I want you to go over was, given that this short list of forces is conservative, why are these conservative forces? What's the criterion that we use for saying that a force is conservative versus saying that a force is not conservative? As you think about that, I want you to think about the example we used on Tuesday. So example of friction and gravity. It's a simple example. It sort of helps you think about what it means for this to be conservative. So here's the sense in which friction is not conservative. When this cart, let me have it start out with some kinetic energy. I push it. So it's moving. Let me actually do this with a block. I think it's safer with a block. I keep worrying that the cart will fall over. So when I push this block, it starts by moving, but then it quickly comes to a stop. What would you blame for this coming to a stop? Friction. Specifically, what does friction do that causes this to come to a stop? Well, friction actually doesn't resist applied force so I apply force for a very short amount of time, and for the rest of the time, I'm not applying any force. So the friction is not resisting applied force. Steven, you're going to say something? So friction force is what is converting the kinetic energy into thermal energy, yes. What's the mechanism for that happening? The thing that we introduced on Tuesday, you had a whole lab about this. Work? Yeah, work. So we say that the friction was doing work, and recall from Tuesday that the reason work is important is it ties into change of energy. In particular here, change of kinetic energy. So as the block is moving from left to right, friction is acting to the left. So the force times displacement is negative, it does negative work, it takes energy out of the block. Yep. So you could point to that and say, that's why friction is not conservative. So friction takes energy out of the block. Now, if you stopped there, then friction and gravity doesn't look all that different. When I throw this ball up, if you stop the motion right here, this is what you see. As the ball goes up, what kind of work is gravity doing? Gravity is doing negative work. So look at the motion of the ball. Is what you see consistent with the gravity doing negative work and taking energy out of the ball? Right? So up to this point, gravity and friction, they don't look any different. They are doing negative work. They are taking kinetic energy out of the object. The distinction between gravity and friction is what happened next. So with the gravity, from this point on, what kind of work is gravity doing? Positive, it's moving downward, and gravity is still pointing downward. So the kinetic energy that was lost on the way up gets returned to the ball. What about with the friction? What happens after this block comes to a stop? Yeah, nothing happens. Wait, what happened to the friction force? Right now it's 0, right? So the kinetic friction force that used to be pointing to the left, it's no longer there once the block comes to a stop. And that's the key distinction between a conservative force and a non-conservative force. And the way I like to describe it qualitatively is that conservative force is predictable. As in, you can rely on it. You can predict what it's going to be, so that when a conservative force does negative work, as this ball goes up, conservative force does negative work, we have some reason to believe that that negative work is not simply wasting the energy. That negative work that was done is stored the kinetic energy into some other form. And because the gravity is predictable, it's pointing downward, constant, I have a reason to believe when the ball comes to a stop, gravity doesn't go away. It continues to point downward. So this ball, as it now moves downward, gravity starts doing positive work. It returns the energy that it stole in the first place. So that's really what makes a conservative force conservative. We call it conservative because whenever conservative force does negative work, we don't look at that negative work done as being energy lost. We associate conservative force with potential energy. So whenever a conservative force does negative work, we don't look at it as being lost. We say when conservative force does negative work, that amount of energy that's taken out by the negative work is stored as potential energy. So this is the expression that we'll use to derive a couple forms for potential energy. So in the lab last Tuesday, you guys are using this formula before I had a chance to derive it. So we'll derive this today, and we'll look at the other form of potential energy, spring potential energy. So whenever with the conservative force, this is what you can say. So this is a new form of energy that we are now identifying and deriving formulas for. We say that the change of potential energy is given by the amount of work that's being done by conservative force. So I would call this negative work done by conservative force. Does it make sense that there's a negative sign here? Yeah, when a conservative force does negative work, do potential energy increase or decrease? Increase, right? So when this is negative, I want the change to be positive. That's why there's a minus sign here. So you could write this out as the change in the potential energy is the negative of the conservative force, dot product with the change of position. So with the gravity, I guess it's easier to see that gravity is predictable, because we do this every time we solve a Newton's law question. We say, gravity is always downward, always mg. So in fact, when we so let me derive this formula now. So using this expression here. Let me give you a slightly more interesting scenario. Imagine I have a slope where I'm raising a block is somehow being moved from this lower position here to a higher position here. Somehow it's being moved up here. So the block starts out at some height. Let me call this initial height equals 0, just to make it easy for myself. Right? No reason to introduce unnecessary numbers. And when the block goes up here, let me say this final height is capital H. Yep. So this is a situation that we know how to analyze. If a block is moving somehow from here to here, then let me make things easier to think through and say that it's almost at rest every single time. Like it's not moving up the hill because I gave it an initial push and then let go. It just starts out at rest, and I'm just pushing it up slowly, so that slowly reaches the top here. So when you think about the situation, visualize it. What you should realize is that there must be at least 2 forces acting on it, right? Yes, because there's gravity pulling it down, mg. If that's the only force acting on it, then it's gonna move downward, right? What are the other forces acting on this box? There's normal force, but when you draw the normal force, that's not enough. Because if these are the only forces acting, it'll slide downward. So what else is there? Yeah, there's applied force. So I must be applying some amount of force to make this block slowly slide upward. So there's all this picture in the background, but what I want you to pay attention to right now is the work being done by gravity. How much work is being done by gravitational force? So I guess the easiest thing to do is actually just go through the math and calculate it. So we want to calculate this expression here, dot product between the conservative force, gravity, and the displacement. The displacement vector here would be something that looks like this. This would be my displacement vector. Yeah? Let's just try applying the definition here and see what we can get. So to apply the definition here, let me copy the figure into clean area here so that I can label things better. So gravitational force vector, mg is downward. Displacement vector, it's going this way. Let me label a couple other things that really should have been specified in the question. Somebody should have told you this angle theta, and somebody should have told you, well, I guess that's it actually. Yeah. So to label that angle theta here, I need a horizontal here, and this would be theta. Yeah. And so this is what the definition tells you, that work done by gravity is equal to force mg as a vector, dot product with the displacement. All right. I guess there are different ways to do it. Let me just try applying the definition just straightforward. Like it says, that mg cosine theta. So let me just do that. Mg, so that's the magnitude, times the distance, delta x, times, when it says cosine theta, is it this theta that it's talking about or a different angle? Different angle, right? It's talking about this angle here. Angle between the two vectors. So let me use a different symbol for this, phi. So it's mg delta x times cosine of phi. I want to express this in terms of theta. In the interest of time, let me do this using some numbers. So you can use angle addition formula to do this purely algebraically, but I think I can illustrate my point better if I use specific numbers. So let me do that. Let me make the numbers easy for myself. I'll say theta is equal to 30 degrees. That will also mean a couple of things because it's a special 30-degree angle. Height h is equal to delta x over 2. Like, I have those nice numbers. So, so if theta is 30 degrees, what's phi? Phi is 90 plus 30, so 120 degrees. Anybody here happen to know what cosine of 120 degrees is? Negative 1/2? Yeah, negative 1/2, right? So when I plug in these specific numbers here, then I get mg times delta x times minus 1/2. And let me plug in what delta x is in terms of height h. So delta x in terms of height h is mg. So I have expression here. So it'll be 2 times the height times minus 1/2. So for this particular value of angle that I have used, the expression you end up with, work done by gravity in this situation, is equal to minus mgh. And what I will state without proving it, to prove it, you have to use the angle addition formula, is that this relationship will be true no matter what angle you use. And this is actually one of the properties of dot product that I didn't have time to get to on Tuesday. The dot product takes the projection of the vector. So when you take the dot product between this displacement vector and this vertical vector, the component of displacement that matters is the vertical component. It's this vertical component that matters, and that's just the height h. And it works for all other angles that you might use. So this is the work done by gravity. You use it here to derive the change in potential energy, gravitational potential energy. So change in gravitational potential energy is equal to minus of all this work done, minus mgh. So these two minuses cancel. And so when there's a change in height of h, change in gravitational potential energy is mgh. And that was the formula that you were using last time. And so that's why you care about the change in height alone, not change the entire distance that you travel over the ramp. Does this example make sense as the potential energy that gets stored as a result of the negative work being done by gravity? Yes, no? And here the confidence is this. So as I'm pushing this up, gravity did all that negative work, taking out kinetic energy that might have gone into the box. The confidence here is this. When I let go of the box, then the box will roll down on its own. So to give you an actual physical example, I have this ramp. So when I have this incline of the ramp, so as I apply a force to push this up, without gravity, when I'm applying force, it would have accelerated upward. But because gravity was constantly pulling it down, it didn't gain all that kinetic energy. So even with all my push up here, it ends up with a 0 kinetic energy. But this is the confidence I have from the fact that gravity is a conservative force. That when I let go of this hand, gravity will continue to act, and it will turn the energy the potential energy that's here into kinetic energy. So I don't have the confidence with the friction. With the friction, if as I was pushing, friction took out all that energy of work that I'm doing, so it gains no kinetic energy. I don't have the confidence that when I let go of my hand, friction will snap it back to where it came from. Like, friction doesn't do that. So that's the key distinction between conservative force and a non-conservative force like friction. And so when you are dealing with a conservative force, You calculate the work done, and you say that gets actually stored into this form of energy because you think you are going to be able to get it back. It's a difference of lending money to a friend who's never paid you back versus depositing your money into bank. Like when you deposit into bank, you think you're going to get it back. So it gets counted as your net worth. But if you're lending money to someone who's proven unreliable, then you don't count it as your net worth because you don't think you're going to get it back. So when we start talking about spring force, the other conservative force we are talking about in this semester, what you will quickly realize is that, well, spring force is not constant. So when I hang this spring here, the amount of spring force that's being applied right now versus the amount of spring force that's there right now, and the amount of spring force that's there right now, are those constant? For those three scenarios, spring force is different, right? Let me draw a figure to help you visualize. So at this very top position, where I hung 0 mass here, how much spring force would you say there is? 0, right? So spring force is 0. Let me hang a 10 gram, I think this is a 10 gram. No, let me hang a 100 gram mass. So at this position where the spring is, what do you think what's the direction of spring force? Upward, right? So so imagine drawing a free body diagram of this mass here. There's downward force, there's gravity pulling it down, but it's not accelerating downward because there's another force pulling it up. That's the spring force. There's the spring force pulling it up. And in fact, based on this diagram, I can say they must be equal in magnitude. So the spring force is upward. And if this is 100 grams, then spring force is approximately 1 newtons. Good. Let me hang another 200 grams so that now this spring is stretched down to about here. At this position, so spring force is still upward, right? What's the magnitude of spring force? I'm hanging 300 gram masses here with a downward weight of 3 newtons. So upward force of 3 newtons, right? So here I have upward spring force of approximately 3 newtons. So this is what I mean. Spring force, it's a function of position. It depends on how far you have stretched it. If you didn't stretch it at all, then the spring force is 0. And depending on how much force it's giving, it stretches different amount. And that's really why I was using spring to illustrate whenever I was applying a force that I wanted to show that I was applying a force. So let's say we want to come up with an actual expression for spring force. Any guesses what that expression should be? So let's say I want to write down an actual equation for spring force. And to say spring force as a vector quantity is equal to something. I think I have some sense that it's going to depend on displacement, because that's what you saw here, right? Depends on how far you displaced it from where it started off from. Anything else it seems to depend on? Oh, so with the mass, so mass is what I'm using to apply a known amount of force. So I could just stretch a spring this way, and spring is applying a force on my finger. It's just harder for you to see that the force that the spring is applying is 3 newtons here. So spring force doesn't depend on mass, because I could be doing other things that causes the spring to stretch. Here, right now, I'm just using the mass, using it to cause it to stretch. Yeah? That's the displacement here. By displacement, I mean displacement of this point here. So anything else it seems to depend on? Right now, no, right? Now, so maybe I want to say this, that the spring force is equal to, let me actually move this over. Spring force is equal to delta x as the displacement. There are actually two problems with writing down this, which is I'm leaving room here to correct it. And can someone tell me what some of those two problems are with trying to write down something that looks like this? It doesn't have a spring constant. So if you have seen spring force in another physics class before, then that's what you're realizing, that there's no spring constant. Let me tell you what the problem that spring constant is fixing. So it's a unit. The unit on the left-hand side, the unit here is Newton. I'm talking about force, right? Or write it out in terms of a basic SI unit. The unit on the left-hand side are kilogram times meter per second squared. Mass times acceleration. Unit on the right-hand side right now, it's just meters. And a Newton cannot equal however many meters. It's two different quantities. On I want the right-hand side, with everything included, to be in newtons. So that's where I introduce a constant. I say, there must be a constant here. Call it K. And this constant must have correct units to turn this meter into Newton. So I guess the constant here must be Newton per meter. Because that's what it should work out to be. Or if you write it out like I did on the left-hand side, then it'll be kilogram meter per second squared divided by meter. So it'll be kilogram per second squared. And in homework questions and different questions, you will see spring constant given in these two different units, either Newton per meter or kilogram per second squared. I think was this one of your exam questions? Exam 1? Yeah. So, it was on your exam 1 because you could have figured this out based on unit alone. Yeah. Okay, so that's one problem fixed. There's one more problem. Yeah, Stephen, you're looking at the directions, right? So when I pull this spring downward, is the displacement downward or upward? Downward. Is the spring force downward or upward? Upward, which means, all right, I have to indicate somewhere here that these two are in opposite directions. So I need to have a minus sign here. So this is something that you might have seen in other physics classes before, or other classes before. If you remember the name Hooke's law, this is what it is. Because a guy named Robert Hooke, who lived in the same time as Newton, was the guy who came up with this. But that's Hooke's law. So this is the spring force, and what this expression is telling you is that spring force it's not a constant. It's a force that depends on position. And what we want to say is that somehow even this is still predictable enough to be considered conservative force. So, in what sense is this predictable? Let me show you a little illustration. I'm going to start it out with up here, right? And if there wasn't a spring force, when I let go, it would accelerate downward, right? Gain kinetic energy. But when there's a spring force, when I let go, this is what you see happen. It slows down, so that after it moves some distance, at this point here, it comes to a complete stop. So that's what happens. So, spring force does negative work. When I lift this and let go, as it moves downward, spring force is opposing it falling down, and it's slowing it down until it comes to a stop here. So spring force has done negative work. It's taken out kinetic energy, and in fact, it has taken out some of the gravitational potential energy also. And when we are calling spring force conservative force, what we are trying to get at is that it's still somehow predictable. In what sense is it predictable? You see it returning the mass back, right? So, after it has come to a stop here, it doesn't remain stopped there. It moves back. And the reason it moves back is that at this position, spring force still acts upward. So that after it's come to a stop, there is an upward spring force, which is pulling it up, which is accelerating it up. At this position, there's also upward spring forces still. So when you look at spring force, look at it in detail, it depends only on position. It doesn't depend on anything else. And that's what makes a spring force predictable. So I want to now make this statement more precise, where I said, conservative force is predictable. Predictable in what sense? Well, it's predictable in this sense. And this is the description of conservative force you would find in the textbook. It's predictable in the sense that it is a function only of position. So that when the mass is at a particular position, you don't have to know anything else to know what the spring force is. Whether it's moving downward, upward, whether it's moving or not, the amount of spring force only depends on position. And that was actually true with the gravity too. And we'll see the universal gravitation a few weeks from now. But gravity, it's technically a function only of position. It just happened to be a constant function. So it actually didn't depend on position, the way you're looking at it. And every one of these forces that are non-conservative force, it's a function of something other than position. Friction, what is a function of other than position? Especially, well, let's think about kinetic friction. Like, what is a function of other than position that we don't consider friction to be a conservative force? What else does it depend on? So, okay, it depends on normal force. But, when you look at this situation here, you would say, all right, the block is here, friction. So friction and, wait, downward is gravity, mg, thank you. Normal force. And so as this moves back and forth, does normal force change? No, so the fact that friction, kinetic friction is, coefficient times normal force. At least in this example, normal force doesn't change, so you don't have to worry about friction being a function of normal force. But you still see a demonstration that friction is a non-conservative force. I mean, if friction is constant, like this formula would have you believe, then shouldn't friction be as conservative as gravity? So there's one more quantity that friction does depend on that's easy to miss. Watch me push this block back and forth. Watch me push it to the right, push it to the left. Is friction the same in both cases? The magnitude might be the same. I mean, friction is a vector quantity. Is it the same in both cases? No, how is it different? Somebody said no. Maggie? The direction is different. Yeah. When it goes from left to right, friction is acting to left. When it goes right to left, friction is acting to right. So friction is a function of not just normal force, it's a function of also, I guess, direction, or one way to mathematically say it is the velocity vector divided by its magnitude. So it does depend on what the direction of velocity is. That's why friction is not a conservative force. What about tension and normal force? In fact, do we even have a formula for tension and normal force? We don't. Tension and normal force are one of those forces that we find them out because they satisfy a particular constraint. It either, tension force, its entire role is that this mass is at a fixed distance from this. And it's whatever force it is necessary for that to be true. So tension and normal force do not have so it can be function of many different things. That's why they are non-conservative. Now, having said that, a lot of situations where you have tension force like here, they end up not doing any work. So here, tension force acts radially from this to this point, right? Displacement is in a direction that's tangential direction, perpendicular to this. So according to this definition of work, tension force is not doing any work in this setup. That's why you have this intuition for where there's tension force, you don't have to worry about energy being changed. And that's true in many of the cases. But I want you to start out from the correct place, that these are not conservative forces. I can always come up with a situation where there is a tension force that's changing energy. There's a normal force that's changing energy. Here's another way to put it. Every conservative force you can associate with the potential energy. Tension force and normal force, there's no such thing as a potential energy that's associated with these two. And applied force, it's not conservative for a very simple reason. It kind of depends on what I want to do. So, when this block is here, and if I don't want to apply any force, then its energy doesn't change. The moment I decide I want to push it, its energy changes. So applied force depends on the whim of whoever's applying the force. That's why sort of by default it's not a conservative force. So, these are the only two conservative forces you will see in this class. But I want you to be on the lookout for more, especially in the future physics classes. When you take physics 4B, you will see that electric force is a conservative force. Magnetic force, surprisingly, is actually a conservative force. And in fact, at a fundamental level, every single force is a kind of conservative force, which is why what we said on Tuesday holds, that total energy is always conserved. You just have to account for all the different forms of energy. But for the purpose of this class, we are keeping two simple ones, gravity and spring force. Any other force you see is not conservative. And the question you should ask is, okay, is that non-conservative force doing any work? If it's not doing any work, then you can say, oh, my energy will be conserved, and that will be one tool you will use in problem solving starting, I guess, next week. Yeah. Questions, comments? All right, I think I have just enough time to derive an expression for the spring potential energy. And this will be first of many illustration for approaching a problem of this type. So I want you to see it done in detail, but since this is the first time you are seeing this, I won't expect too much. But I want you to look at this 2 years down the road when you have transferred and you are taking engineering classes, that this was the first example where you saw this particular approach being used. So we want to figure out change in the, I think I can remember this, so let me erase all of this. So we want to figure out what is the change in the potential energy due to spring force. So you might start out with the definition that I wrote down earlier, that it's a negative of the work being done by spring force, or the spring force dot product with displacement. So here's one question we could ask. Actually, let me use a simulation for that. It's going to be quicker that way. So this is one of the simulation websites I like. You have seen it before. So if I hang a mass here, comes to a stop somewhere, then I want to know if I stretch it out or compress it, then how much work will the spring do? So let me use this example. Let me make this move super slow and make this friction 0. So I want to figure out how much energy gets stored into spring potential energy as I drop it from here down to, down to when it comes to the lowest point. So as it goes from here to the lowest point, I want to see how much work is the spring force doing. So from here to here, I want to see how much work is the spring force doing. So I might start out with writing this down, that work done, or the potential energy is the work done, force times the displacement. But when you write it out, you run into a little bit of problem. As in, let me write out what mistakes someone could make. So this is a mistake that someone could make. You see this, and you write this out. So minus spring force. Hey, I have a formula for spring force. So I'm going to write it in here. Minus K delta X. Dot product with the delta X. Hey, delta X, dot product with the vector itself. I think I know how to do that. That's just the magnitude squared, right? So you write down, minus minus. So it's a plus K delta X squared. And you're so proud of being able to work all this out. And then when you look up the actual answer, you realize you are missing a factor of 1/2. What happened? It's the same vector. So here, the angle between them, theta, is 0 degrees. So cosine of 0 is 1. So what did I do wrong? Something was done wrong here. There's a mistake here. What mistake did I make? So this is a common problem you will encounter in physics. And I really should have recognized this from the beginning, that this spring force is not a constant force. It's a function of position. So as you think about what force would I plug it in here, what you have to look at is, well, you have some idea how much force is here, right? The amount of force that's here. Is that the same amount of force due to the spring when it's up here? It's not, right? Up here, this is where it's not on, where spring is not stretched. Here, the spring force is 0. Down at the bottom is where spring force is at maximum. This formula that you have kind of assumes that force will be constant. And the moment the force is no longer a constant, you run into a problem. So let me describe the approach that we use in physics. The approach that we use in physics is this. You take this entire interval delta x, and you imagine breaking it up into tiny little pieces. You imagine breaking it up into tiny little pieces. And for each one of these pieces, let me call this dx, infinitesimal, that you might have seen in your calculus class. For each one of these little tiny interval, we can now say that over this tiny interval, force is constant. That we can actually use this formula once again. So this is the place we start out with. We say that instead of trying to do this all in one step, we break it down. So I don't know what the total change of potential energy will be, but what I say is that I know how to write down small change in the potential energy. Small change in the potential energy, I know that must be minus the force at that particular position within that small interval times that small interval. And the approach we take in physics, in problems like this, which you will see over and over with different types of problems throughout your 3 semesters of engineering physics, is that we figure out what happens with the infinitesimal interval, and then we add it all up. What mathematical procedure did you learn in math class that does that, where you calculate something for an infinitesimally small interval and you add it all up? So you could do it as summation. That's when these intervals are not infinitesimally small, when they are finitely small. As you make the interval go to 0, what happens to the summation? So the sum doesn't go to 0. So in your calculus class, this would have been introduced as a Riemann sum initially. So you take the Riemann sum, and you make the interval infinitesimally small. There's a name for this procedure. How many here remember hearing about Riemann sum? The phrase, okay. So in what context was the idea of Riemann sum introduced?
To approximate.
What are you approximating?
Area.
Area, okay. If you wanted to calculate area some other way, how would you do it?
The
Integral, yeah. So this is where, the mathematical procedure for doing the calculation we want to do is the integral. I don't know if I told you guys this in this class or not. Calculus was invented for physics. So when you learned calculus in your math classes, you might not have known what all those rules you are learning were for. Well, it was so that you can do physics. I mean, Newton invented the calculus so that he can do physics. I mean, that's one piece of history I actually get right. So here, what we are going to do is we are going to do an integral. I see that I have only 1 minute or so let me wrap up here. So we are going to do an integral. I like to do all my integrals as a definite integral in a physics class. So it's going to go from x equals 0. That's what I'm calling x here. X equals 0 to some final x final. So it's going to go from x equals 0 to some final value, x equals 0 to some final value. Let me plug in what the expression for force is. That's so 0 to final value. Expression for force is minus k times dx. Delta x is just x. Displacement is from 0. So minus from this minus kx dx. Everyone here knows how to do this integral? Yes? Yeah. Minus kx, because that's the expression for the force. So I include the minus sign to indicate the force is pointing upward as x goes from, yeah. So write it all, so minus minus, it's plus. So let me pull out the constant factor, plus k, going from x equal to 0 to final, x dx. What's the antiderivative over x? X squared over 2. So this integral evaluates as plus k times x squared over 2, evaluated from 0 to x final. So that's where the factor of 1/2 came from. So it's 1/2 k x final squared. And this is the formula for spring potential energy that we are going to be using in different problems rest of today and after your evaluation, rest of today and next week. Yeah. So you will see this approach in different contexts, maybe 1 or 2 more times in this class, and you are going to see this just over and over in physics. And the sooner you catch on to what we are doing here, it'll make things easier for you. Yeah.
So yeah, this is a fairly common setup that we fairly commonly consider. So without further ado, let me just set it up. So this is mass on a spring. And do I want a larger mass? I think it's gonna be more fun with a larger mass. So let me have a slightly larger mass hanging here. Oh wow, that is large. Let me see how big the other mass is. Somehow they must have different densities. This is lighter. Okay, I think I can work with this one. So this is the kind of setup that we often deal with when we have. So we have now introduced the work and energy, and we now treat springs with the spring potential energy that helps us analyze the dynamics of the thing. So that, like, if someone says this spring is pulled down by this much, you let it go. How fast is it moving when it says some different positions? That kind of questions. It's something that we can now address. And as you approach a situation like this, there's one way you can approach it, which might be the default way to do it, might even be the kind of the simplest approach in some sense. But I want you to show you a way in which this analysis can be simplified and justify that simplification. So let me start out with how some people might address this setup. So in this setup, you can treat the gravitational and spring potential energy completely separately. That's nothing stops you from doing that. And one way to do that might be you have, so this is your spring's equilibrium length. And as you hang this mass, you see this height reference here. Let's keep this reference here. So you can say when the mass is at this height, there's some gravitational potential energy. In fact, that's what the graph on the left is showing. That when this is at this height, I pause the simulation, it's showing, this mass have this much gravitational potential energy. And at this position, it has 0 spring potential energy because the spring is at its equilibrium position, equilibrium length. And as this mass moves downward, its gravitational energy decreases. In fact, it decreases linearly until it's at height 0, and then it goes negative. I think all this people have seen before. And another thing you also see is that as this spring stretches, the spring potential energy increases as a the displacement squared. And you can also push it up and it does the same thing. Or it also increases it. Spring potential energy, it increases either way to pull. Now, that separated treatment is something you can do. You are not forbidden from doing that by any means. But in some sense, it's more complicated than it needs to be, because how much the spring is stretched and whatever the height of the mass is, that's going to be two things that are actually tied together. So it's going to be only one thing. And so to be treating them as two separate things, there's some sense of inefficiency there. And the other thing is, the direction of change of either the gravitational or spring potential energy alone doesn't really tell you how your total potential energy changes. So it doesn't tell you how your kinetic energy, which is the mechanical energy minus the total potential energy, doesn't tell you how your kinetic energy would be changing. As a kind of static example, watch as I slowly pull this down. You see that so here where it says total energy, right now it should be the total potential energy. As I pull this down, you see, oh, my total energy is decreasing as I pull the spring. So you might wonder if that's always going to be that way. And then as you keep pulling, it's not. So around here is where your potential energy is at a minimum, because as I move this, it doesn't really change. Now, as I pull it even farther, the potential energy is increasing. So there's a different stretching of the spring. There are different things that's happening. And you can almost see that here. Let me, in slow motion, run the simulation and watch what happens with the kinetic energy. So as this, and actually let me get rid of damping. As this falls, you see the kinetic energy increase up to a point. And this up to a point is where your total potential energy is decreasing to a minimum. And past that point is where you see the kinetic energy now start to decrease as the total potential energy increases. And when you look at motion, there is an aspect of this that at least reminds me of a pure spring motion. As in, if somehow I could treat this combined potential energy as one potential energy, then then it would simplify this analysis, because instead of tracking these two separate potential energies, it would be nice to be able to say, instead of this was my equilibrium length, it would be nice to say my actual spring equilibrium is here. This is my equilibrium length. And when I pull my mass from this position, and that increase in potential energy, if I could put all of that into spring potential energy, then I can describe this oscillatory motion much more simply as oscillation of just a spring on a mat or mass on a spring around this equilibrium position. That's what I would like to do. And I think that's the kind of thing that we need to justify. We need to prove that that kind of consideration, thinking of the combined gravitational and spring potential energy as one spring that has a slightly different adjusted parameters from original spring. I think that's something that we should be able to prove. So let me do that. This is what I'm gonna do. I think I can try to describe my setup of a spring here. So let's see, where should I start? So I have a mass on the spring, and let me start out with the original description, because that's the description that I know is valid. I don't have to talk my way out of anything. So so you have this, which is I have a mass that is getting displaced by some distance delta x, and this parameter is going to connect to the spring potential energy. But this parameter it also actually connects to gravitational potential energy. And in this case, for the sake of simplicity, instead of using this as my height equals 0, let me use this also as my height equals 0. And I am allowed to do that because with the with any potential energy, but especially gravitational potential energy, what's meaningful is a difference in potential energy. So you can always change your reference point. So as this mass falls, your gravitational potential energy, this mgh, is going to become more negative as my h is it's equal to minus delta x. So as my delta x increases downward, my gravitational energy will it will decrease. It's decreasing from 0 down into negative values. So all of that is fine. I can just set my height to be 0 at the equilibrium length position of the spring. So with that description, let me write out the expression for let me work with the total potential energy, because I think what I want to be able to say is regardless of where this mass is at, there's some way to translate what the description of the potential energy of this system would be with the separate consideration of gravity and spring to what the combined spring potential energy would be. So let me write down the expression for the total potential energy. That's going to be the sum of my gravitational potential energy and the spring potential energy. And I think I can write both of them in terms of this parameter delta x. Let me do that. So mg, and I'm going to make a delta x so that this direction is positive direction, because that's where I'm stretching, elongating the spring. Mg times minus delta x plus 1/2 spring constant times delta x squared. And if you're just looking at this, you might think, that looks nothing like so if I'm somehow trying to say, oh, this is some kind of a new spring force, well, this has to take some kind of form of 1/2 k delta x squared. It needs to have this term. And what I see here right now, it looks nothing like this. So, okay. Now, there's a pure mathematical way to do what I want to do next. I think it's called completing the square. But since this is not algebra class, it's a physics class, let me find a more physical justification for what I want to do. So for a physical justification, I think what I'm looking for first is my new equilibrium position. Because one thing that I know definitely changes between my old spring and my new spring is that equilibrium position is not at the same position. The old spring equilibrium position is here. My new spring, the equilibrium position should be right here. So, and that's significant that that where the equilibrium length position of the new spring would be at this position. So let me give it a special symbol. So I can call this a displacement. Let me call that delta x equilibrium. It's somehow a significant position. And this is the position where I would like the equilibrium position of my new spring force to be. So, okay, and I think I can actually even come up with an expression for this. Quick Newton's law consideration, draw a free body diagram. At that equilibrium position, there's gravity pulling down on the mass. There's a spring force pulling upward on the mass. And because the acceleration is 0, the spring force, which is equal to the magnitude y, which is equal to k times delta x equilibrium must be equal to mg. That's how the acceleration would be 0 there. So I can actually solve for this. And solving for the equilibrium length, I get mg over k. So this equilibrium length, it has an expression in terms of parameters already in the setup. So okay, I have that. Yeah, so that's the new equilibrium position. So okay, let me think around that. So I guess before I was saying how I want this to be expressed as some kind of new and improved spring potential energy. And originally I was saying, hey, I want this to be k times delta x squared. But if I think about it more, I don't think I want that, because where I want my spring potential energy to be 0 is not where delta x is equal to 0. Like up here, that's not where my new spring potential energy would be 0. That's actually at quite a bit of an upward distance from involves quite a bit of compression from where the new equilibrium length is. So I think for the potential energy of my new spring, I actually want this energy to be minimum, not at where delta x is equal to 0, but at where delta x is equal to delta x equilibrium. And one way to get that is to do a little bit of translation, transformation of function. And let me write it down, and we can just double check to make sure that it looks right. So the transformation I want to do is this. Where I see delta x, I want to replace it with the delta x minus delta x equilibrium. And then the square is still there. And we can check that. So the way we would check is we can plug in what we get when we plug in delta x equals delta x equilibrium. Then I have delta x equilibrium minus delta x equilibrium, 0, 0 squared, 0. So 0 seems pretty small. So good. So this is what I think I can show my new spring potential energy to be. Let's double check that. So what I'm gonna do is this is some parenthesis thing squared. So let me expand this out, compare the expression I get against this original total potential energy, and see if there are any adjustments I need to make. So I'm going to expand this out. My new spring potential energy, let me call that, new spring, is equal to 1/2 k, and as I do this square, I'm gonna have delta x squared, okay, plus I'm going to have minus delta x equilibrium squared. So when I write it all out, distribute 1/2 k, it's gonna be 1/2 k times delta x equilibrium squared. Okay, and I have the cross terms, the terms you get from multiplying this with that and this with that. There's two of them, and it's minus, so 2 times 1/2, so 1 times k, and the cross term, delta x times the delta x equilibrium. I do see some matching terms, and that's encouraging. This 1/2 k delta x squared, that matches with that. Great. So far, so good. And I think none of these look like those. Well, so I have a one term. So remember, delta x is a variable, so you have to treat it carefully. And I have here one term with a linear term of delta x, and I do have a linear term of delta x here, and they are both have negative sign in front of it. It would be nice if I could somehow show that this term is the same term as this. And that's where this comes in useful. I can substitute this in for delta x equilibrium. So let me just do that quickly here. Rewriting this, I get K times the delta X times mg over K. K is cancel. I have delta X mg, and that is exactly that with the minus sign there. So great. I have these two matching terms, and that's all the terms. I have this expression here that didn't match to anything. So initially it might look like I have failed in my task, but I want you to look at this expression carefully. Consider this. Is there any variable in this expression? There isn't. K is constant. And this delta X equilibrium, that's also constant, which can be expressed in terms of constant. So this is as though, so my initial guess here, it was close. It was close in terms of in what form, in terms of delta X, it depended. In what terms of the variable it depended, it worked. But I missed out on a little bit of an offset. So there ought to be an offset, plus, let's see, yeah, sorry, I'm trying to formulate this correctly. So the way I would formulate it, I want some way to relate this original total potential energy to this new spring potential energy. And the way I would say this, my new spring potential energy can be expressed in terms of the old total potential energy, and then plus some offset. There is a constant offset between this expression here and this expression here. The constant offset here being 1/2 K delta X equilibrium squared. And remember what I said about potential energy earlier. The only thing that's meaningful about potential energy are always differences. That's what gives change of kinetic energy. That's what results in all the dynamical stuff. So if the only difference between our old representation of potential energy in a system like this expression here, this expression here, the only difference between that and this spring-like representation, this one, if the only difference is this constant offset, then these two expressions for potential energy in terms of the quantity delta X, they are functionally equivalent. Any kind of analysis you can do using this. You can repeat the exact same analysis using this. The only thing to be careful of is if you calculate this absolute potential energy under one representation, you have to be aware that absolute potential energy might not be quite the same in the other representation unless you make this adjustment. So this is my proof that when you have a system like this, you can treat it like a pure spring energy system. And the limitation that you see mentioned in the other video, where I say, oh, you can't do that in this situation, is you have to be able to always tie this extension or stretching of a spring. You have to always be able to tie that with a gravitational potential energy. You have to always be able to say this. And in situations where you can't, maybe the mass comes off of the spring, then you have to treat them separately and just analyze in that way. Because when the delta x, when the stretching of the spring decouples from the height of the mass, then all right, yeah, this representation depends on those two things always being tied. Yeah. So yeah, that's the proof. Or something that I am calling proof. I don't know if it's a formal proof. So and I, from time to time, I will use this shortcut because if I know mass is always going to be attached to the spring, then sometimes it's nice to be able to just treat that as spring dynamics without worrying about there being a constant gravitational force.
Oh, let me do the example of problem 10, because this is something that's already familiar to you. You have dealt with it in the context of kinematics. And what we are going to do now is we are going to re-approach this old question with this new tool of energy. So we could have done this question actually on Tuesday, but so that question doesn't use any of the spring potential energy. It only uses gravitational potential energy. But let's talk about it. All right, let me draw the picture on the board. So it describes a ball being launched with some initial velocity v0 at some angle theta above the horizontal. Is that the description it's using? Yes. And here's the ball is being launched at some height h. And it says it goes through all of this and then lands somewhere here. And it asks a couple of the questions. Let me get to the part that you can answer based on, I guess that's part A. So here's the question that it's asking. As the ball lands, so it's going this way, it has some final speed. It asks, what is the final speed of the ball? And how would you have approached this question if you were doing this in kinematics with the projectile motion? Like, how would you figure out this final speed here?
Find the time it takes to go from that point to that point.
Okay, you could find the time. Let me tell you a little shortcut. Tikal, you go. Well, no.
Fixing up what it says. Well, you know your initial time, your initial velocity is 0
Mhm.
because of the top of the arc is.
Okay. So you guys will always want to, let me show you a shortcut that doesn't involve going through this. I can actually go all the way from beginning to the end. I only have like 2 minutes, so let me do it that way. It's quicker. So this is how I'm going to do it. I'm going to break up this into components. So define x and y coordinate. So initial velocity is going to have x component, and it's going to have y component, right? Final velocity, same thing. It's going to have an x component and the y component. Do you know how? So the reason I don't want to find the time and all this stuff is that the question is not asking about the range. It's only asking about the speed. So I want to say, all right, can I relate this directly to this? How are they related? They're the same. That's one of the properties of projectile motion. All right, I know the x component. That's great. Now can I relate this to this directly in a single equation? PHYS squared formula? What? Yeah, I can use PHYS squared formula. I can treat vertical motion like a 1D motion with some initial velocity, displacement, and constant acceleration. So let me write that down. I can say v final y is squared is equal to v initial y squared. Now I have to be careful. Displacement is downward. Gravitational acceleration is also downward. Oh, so it's going to be positive, plus 2 times g times h. Good? All right, so that's my v final. If I want just the component, then it'll be square root of all of this. Now, let me write out what the final speed v final is using Pythagorean theorem. When I do that, this is what you get. V final squared is equal to the x squared, or that, v final squared is equal to x component squared plus y component squared. So it's going to be v naught x squared plus this thing squared, so v naught y squared plus 2gh. Now, this is where if you recognize this, you can write it down even simpler. You can write it down as equal to V initial squared plus 2gh. Right? This is based on kinematics alone. Now, let me show you the connection to energy in this single last step. So, I wonder, can I have done this problem using conservation of energy? Yes, you could have. And the way you would see it is you would take this entire expression and multiply by 1/2 m, which you might not be sure why I'm doing that, but that's something I can do, right? Like nothing stops me from multiplying the whole equation by plus 1/2 m, where m is the mass of the ball. And when I do that, this is what you end up with. This whole thing becomes let me put this on the left-hand side. The left-hand side is 1/1/2 m v naught squared plus 1/2 times 2, so 1 m g h is equal to 1/2 m v final squared. 1/2 m v final squared. So you have seen some of the energy formulas. As you look at this expression, do you recognize some of those energy formulas? What is the first term telling you? It's telling you the initial kinetic energy. What's the second term telling you? Yeah, initial potential energy at this height. What is the last term telling you? Yeah, final kinetic energy. And I guess you implicitly say here potential energy is 0. So yeah. So the expression that you get using kinematics is equivalent to the expression you would get using conservation of energy. So yeah, now the difference is the kinematics is hard. A lot of people struggle with it. I see semester over semester. A lot of people forget to go through all of these steps. With energy, it's a single equation. So all the questions that you thought were difficult using kinematics, it's going to get easier when you use energy conservation. And you will see that next week when we go through more conservation law problems, and we'll introduce one more conservation law that you will need as you go through these problems. So, all right.